All right. Good morning, everyone. First of all, is my mic too loud? Probably. Reduce the volume a little bit. Okay. Maybe that's better. All right. So, welcome to 4510 Heat Transfer. I'm Professor Sitaraman, Satya Sitaraman. I'll write out my name. There were 10 of me, and at the last count I saw there were 7 more after me. So it beats me. None of them related to me, of course. Not yet. So, I hope you have been able to access the Carmen page. I have the syllabus put up there. And there is an exhaustive set of list of topics and so on. What I want to do, first of all, is to tell you all that you're on camera. You're not being recorded, of course. I'm being recorded. Once the lecture is over, sometime later this afternoon, I will upload the lecture videos so that people who are unable to come to class, and there's quite a few of them, unfortunately, they will be able to access it, and so will you all be able to access it as well. Okay, so this is for the benefit of everybody. What I want to do today is I want to walk you through some basic aspects of the syllabus, okay, and then we will go into an introduction into heat transfer. All of you can hear me loud and clear? Am I audible? Can you understand what I'm speaking? No confusion whatsoever? Okay. In case you cannot understand what I'm speaking because I'm double masking, I don't know if a triple mask will help either, but I'm trying my best. If you cannot understand what I'm saying, please let me know. I'll be more than happy to repeat it, okay? And the same goes for my writing on the chalkboard as well. As you can see, I'm quite old-fashioned. I like using the chalkboard. I have also taught online classes using other devices, so if push comes to shove, 2 weeks later, if things change around, please be prepared for all of us to go online too. Okay? The policy as of now is we will be in person. This is not a policy that I have written out. It is for everybody. Okay? All right. So a little about me. Just for one particular lecture today, I'll be doing a lot of talking. And after that, we will be going into equations and problems and so on, concepts and so on. So there will be more of a conversation between the two of us. Okay? A little about me. I've been a faculty member here for the past, I don't know, since 2009, 2010. I got my PhD here at Ohio State. I was a postdoctoral fellow for a couple of years doing research in heat transfer, well, you know, heat transfer. And then after that I started teaching at Ohio State, conducting research as well. My research is in the area of mechanics, deformable body mechanics, plasticity, and so on. But in my former life, which was 10 years back, I was also a researcher in the field of heat transfer. So which is why I'm here. Okay. I teach courses in several areas, mechanics, dynamics, and statics. The common joke is that I see a lot of you when you come and enter the ME curriculum, teaching you statics. Probably some of you took my statics and dynamics classes. At some point I can see some people nodding their heads. I also see that, you also see that I teach the last class for your ME career here as an undergrad. Right? This is typically your last big ME class and the hardest one. I want to be very forthright with it. If you think dynamics was hard, you're in for a rude shock. Okay? So this is going to be multiple times harder. That does not mean that it should not be fun. Okay? You're all ME graduates, so you're masochistic in some way. So we will try to make it as much of a fun experience as possible. Okay? And I teach courses in several other areas as well. There are probably 4 courses that I have not taught in your curriculum, and I don't want to teach them either. Okay? Measurements being one of them. Alright, good memories, I see. Okay. Alright, calm down. Okay, so going back to the syllabus, so that's a little about me, and hopefully you'll come to know more about me as we go on in time. I'll get to know all of you as well, my hope. I have office hours and so on, which are all conducted online. Okay, so but feel free to come to office hours and so on. And I want to talk briefly about the syllabus. So first thing, my email address .11. Please email me at osu.edu, not Buckeye Mail. Okay, so at and the not the reason being Buckeye Mail is not supported by my department, so it's an unofficial email address for me. At osu.edu is my official email address. So you email me there, I'll be much more faster in my replies to you. Okay. My physical office is probably not of much importance in this semester, though I sit in Scott Lab, East 502, 5th floor. So in case of an emergency or something, you want to contact me in person, please do visit. If I'm around, I'll be able to help you. Okay? My office hours are listed on Carmen. Fridays is when I spend the bulk of my office hour times, from 10 a.m. to 11 a.m. It's there on your syllabus, okay, so I'm not going to repeat it. 10 a.m. to 11 a.m. and then on evenings from 4 to 6 p.m. Fridays are my office hours, and your homeworks, you'll be seeing plenty of them this semester. They will be typically due on Sunday night, 11:59 p.m. But please do not start your homework on a Friday. Chances are you will not get it done. Okay, please, this is my request to you. But during office hours, you can come, you can be a fly on the wall, you can just sit down and see, okay, what are the questions others are asking. If you have a question, feel free to ask me. Do not hesitate to ask me questions. There is nothing that is a foolish question. I have many questions that probably others will consider foolish, but it's my knowledge on the line, it's my life on the line, so I want to know more, right? So that has to be your attitude, okay? So there's nothing wrong in asking questions. Don't hesitate. Office hours are the best times to ask me questions on how not to solve the homework problem. Okay? You can ask me questions on conceptual issues. You can tell me, okay, hey, this is the approach I've taken to solving this problem, but it doesn't seem to be the right way. Can you show me why, or can you tell me why? Can you pinpoint maybe places where I'm stuck? Okay, things like that. Do not come to me and tell me, hey, I don't know how to solve this problem. My answer is neither do I. Okay? Because most times, I design the homework problem, my special gift to you. I don't have the solutions because I haven't gotten around to getting the solutions out. But at the end of your homework, when everything is due on Sunday night, typically on Monday morning or Tuesday morning, I'll post the solutions. So that's when I actually start working on the homework. Just like you, I start on a Friday night because we have nothing better to do, right? But of course, I do start a little early. So make an honest attempt on the homework. The homework will be challenging. They are meant to provoke your curiosity on heat transfer. They are not meant to make you do grunt work. I don't like homeworks of that kind where you just keep doing the same problem 5 times. That's not the kind of problems I give in my homework. Okay, and you'll get it. Incidentally, there is a homework due this Sunday. It's going to be a very gentle loosener. Okay, I just want to know about you. I'll have these questions out on Carmen. Whenever I set up a homework assignment, whenever I submit the questions on Carmen, you will get an email from me. Okay, please make sure you read it or at least give it a quick glance. So that's it for the homeworks. You'll also have in-class quizzes, pop quizzes. This is how the quizzes work. Towards the end of lecture, I'll give you a problem. Very short, quick problem. You don't submit it right away. You take it with you. You give it to me in the next class. The next lecture begins, and you'll be submitting it online. I don't accept any paperwork. Everything is online. Exams are online. Homeworks are online. In-class quizzes, they are approximately not in class. They are slightly out of class quizzes. So you'll be submitting them in the next lecture, the beginning of the next lecture. Okay. So that's it. The homeworks and the quizzes. Then you have midterm exams. Midterm exams. Here is the deal with midterm exams. So, for example, let's take midterm 1. It will be held on February 17th and 18th. Okay, for example, and you can see the actual dates on the syllabus. So, February 17th and 18th. It does not mean that you have 2 days. No. On February 17th at 10 a.m. I open up the exam. On February 18th at 11:59 p.m. I close the exam. Between these 2 days, you have a window of 4 hours. So this is a timed exam. This is not a 2-day long exam. 2-day long exams are really painful, especially in heat transfer. So 4-hour exams are better. It does not mean that the exams are going to take 4 hours. It means that it will take you probably an hour and a half. You have some extra time so that you can account for maybe internet issues or several contingencies might arise. So you want to make sure of that. So this is a 4-hour window in between. You'll be writing it as a Carmen quiz. Okay? You click the exam on Carmen, your clock starts, and it ends once you're done with the exam submitted before the 4-hour window. Okay? As you may know, some of you may know, some of you may not have taken my courses in the past. As you may know, though, or you'll probably get to know very well, I don't accept late work. Absolutely, never, ever. In my career of teaching since 2009, 2010, I have never accepted late work. I have never accepted shoddy work. And I make sure that whatever I do has my utmost effort. And I expect the same from you. Okay? So please no late work. The same goes for midterm 2 as well. So blah blah blah, final exam. Final exam, I haven't thought about the amount of time I want to give you. Probably more than 5 hours, 5 to 6 hours. Once again, these exams do not take 4 hours. Please, don't take it that way. This is just to alleviate the stress of writing these really difficult exams. The exams are not difficult either. They're fairly straightforward. If you have come to class, if you've been a warm body in class, if you've been doing your homeworks properly, you should be in good shape to write the exams. Okay? So no surprises, anything of itself. Exams are open book, open notes. No collaboration. I have a check account. I have an account on Course Hero. Everybody in my department does. So if questions are asked there, we get to know, and we also know who asked these questions. And we have taken it upon ourselves to make sure that there is no academic misconduct of any sort that happens in our classes. There is no room for academic misconduct. I appreciate ignorance. I don't appreciate cheats. Okay? So please make sure you're above board. I trust you. I'm not going to have my camera turned on or your camera turned on. I trust you. You're all proud students of Ohio State. You're proud human beings, whether you're students of Ohio State or not. You're proud human beings. Make sure that the work you present is your original work. Take pride in your work. Okay, that is the only way to survive. Alright, so that's it for the exams. Final exam, once again, open book, open notes, no collaboration. If you're an engineer out in the field, you will have the capability to look up on resources. So I want the exams to be something of that sort as well. Okay, where you have the capability to look up resources if you're stuck at a point, but you present your best work. Okay, the exams will not be straightforward, but they're also not inordinately difficult, miserable things. We want it to be a fun course. We want it to be a challenging course. Most of all, you want it to be a useful course. You want to say that, okay, hey, I do heat transfer, I know this thing damn well. That's the attitude we got to have. Okay? And if you look at the list of topics, please take a look at the list of topics. Just read them out aloud, even if they don't make much sense at this point in time. You'll see that we have a lot of topics, which is typically in every course that you've taken probably so far. As an instructor, I reserve the right to make sure that there are certain fundamental topics that you learn very well, and there are other topics which may be, okay, it's good to know this, but it doesn't change your life if you don't know it. So I'll make sure that I'll cover the fundamental topics. If there are certain things that we may not get to, that is okay. Please trust me that whatever we go through in this semester will be very useful to all of you. Okay? We are in this journey together, whether you like it or not, you have me here. But hopefully we grow on each other, and in a good way. I'm always there to help you if you have conceptual issues, if you're struggling with something, if some concepts just don't click at all. I mean, when we go to radiation heat transfer, radiation is really obscure. You see it everywhere, but you don't see it. So sometimes those things may not click that well. Talk to me. Talk to me. Maybe I may not have answers for you right away. Maybe you ask me a question in class, I might say, okay, hey, this is going to take a little more time to explain. So perhaps we can talk maybe during office hours, or maybe we can set up a time to talk on Carmen Zoom. Okay? 3 things I want to mention on the COVID-19 or whatever thing. First thing is, I know that there is a chance that some of us might get affected by it. I'm as much susceptible to it as you are. In the off chance that I face a personal situation which prevents me from coming to in-person classes, as an instructor of an in-person class, we have, as a faculty member of an in-person class, we have up to 8 hours of lectures that we can offer online. This is the worst case alternative. If I'm sick, I'm going to say, okay, hey, I'm sick, I'm not going to come and infect all of you. I'm going to come and teach that class on Carmen Zoom. I'll let you know beforehand. This is not going to be for the entire semester. This is just going to be for the recuperation period. Okay? That's the first thing. Second thing is we're recording all the lectures. So in case you end up in a situation that prevents you from coming to class, you can have access to the lectures. I'll be posting lecture notes as well. They will be slightly elaborate, but don't expect granular details on what we're talking about. You have the textbook for that. And I want to talk about the textbook in the last thing that I want to talk about. And the third thing about COVID is, I know that many of you want to ask me questions after the end of the lecture. I don't mind it, but let's keep our distance. Okay, so if you have questions, you can come and sit in the first row here. I'll be standing here. Feel free to ask me questions. Typically, I linger around for a few minutes after class. I'll be happy to answer something that's good. Okay? During class, I expect us all to be courteous to each other. We are living in difficult times. We want to be inclusive of each other's diversity, each other's opinions. Thankfully, this is a science-based course, so this is not a subjective course. So these are not my opinions. I present facts, unquestioned facts. Okay, so there is no room for disruptions here. But please be aware that we want to behave in a courteous manner. If you want to go take a bathroom break or something, please make sure you don't disturb the entire class. Go gently and open the door. I've been told to tell you this. Please make sure you don't eat food in class. Okay? I've told you. Okay. Textbook for this course is on the syllabus. Try to get a copy of the textbook. Try to get an older edition. You get them for quite a decent amount of money on online or something. The textbook is a good one. What do you know, right? It's got a lot of good examples in it, and I think some of the topics that we talk about, if you want more in-depth physics-based approaches to these topics, the textbook is your go-to thing. Okay? Please try to have a copy of the textbook. Homeworks will be assigned by me. I'll be uploading the figures and everything, so you don't need the textbook for solving the homeworks. But a textbook is a good resource to have. It's actually a very useful textbook, in my opinion. So that's my introductory spiel. And I want to see if all of you can still hear me clearly. Back of the rooms, sides. All of you can see the board properly on the sides and so on. All these ways. You guys are all fine. I think you can see the board. If my writing is not legible, if you want me to write a little bigger, let me know. More than happy to comply. These are all small things. Don't worry about it. I'm not going to get offended or anything. If you have questions, feel free to stop me and ask me. If it's a quick answer, I'll give it to you. If it's a quick clarification, I'll be happy to do it. If it's elaborate, we may have to take a step back and talk about it in detail later. Okay? All right, so any questions? Yes.
You guys are in-class quizzes. Were those in lecture online or before class?
Oh, let me give you an example. So at the end of today's class, I mean, we're not going to have a quiz today, but at the end of today's class, probably I would have started solving a problem. Maybe I won't get time to complete the problem. I'll tell you, okay, hey, take it. You know the steps to do the problem, solve it, upload it at the beginning of next lecture. And I'll upload the solution to the problem as well. Or I might just tell you, okay, hey, this is a brand new problem, give it a crack. We're going to come back in the next lecture and maybe look at the problem again. Okay, so things like this. Okay? Any other questions, please? All of you still want to be here? You can't see me smile, neither can I see you smile. But I hope the tone of my voice implies that we are all in this together. We are learning something useful. Okay, towards the semester. The material can get very intense. The math is complicated here. Heat transfer is not engineering; it's physics and math. Okay, what we want to do. I'm not a physicist, of course. I was a mathematician before I became an engineer, so there is that. I will do the math properly, with a good amount of rigor, but I also want to make sure that we don't lose sight of the bigger picture. Okay, you can have the tendency to get lost in the equations. That's not our intention. There are certain derivations that I'll do in class. There are certain derivations that I might have you do as a homework. But most of the time will be spent on solving problems with very practical aspects to it. Okay? Last questions before we begin the lecture? let's begin our actual class for the day. I want to do something very gentle today. I just want to give you a brief introduction to heat transfer. Okay, so today's class. My shorthand for heat transfer, HX. Now, heat transfer, why is it useful? In some ways, this is a kind of a no-brainer because the moment we are born, we all become the most spectacular heat engines. Right? I have blood coursing through my veins. There is conduction heat transfer taking place across the veins. I'm walking here. There is relative motion between the air surrounding me and my body. There is convection heat transfer taking place. Maybe I'm hot, the room is cold. The room is hot, I'm cold. There is a heat exchange taking place. I'm talking to you, I'm looking at you, I'm radiating energy because I'm at a temperature greater than absolute Kelvin, 0 Kelvin. Good energy or bad energy, that's up to you. But we're all radiating energy in some way. Okay? So heat transfer, in my opinion, is the most fundamental of courses. It's as fundamental as, for example, mechanics of materials. And my interpretation of heat transfer is more from the perspective of a mathematician, lesser as a perspective of an engineer, but I always believe there is a good cohabiting marriage between engineering and math. And that's what we will be looking at in this particular course. We'll be looking at many useful things, different types of heat transfer, different devices. You have fins sticking on engine blocks. Why are they there? What do they do? You have an ice skating rink. There is a large amount of heat transfer that goes place in there, right? You have the cold floor, you have the roof, you have people sitting in the stands. So what the hell is going on there? Different modes of heat transfer there. Heat exchangers, all those old radiators, pipes and so on, cooling systems, fantastic things. These are all applications of heat transfer. You open up your computer, you're going to see a fan there, natural convection, forced convection, everything is taking place. So these are all very nice applications of whatever we're going to learn here. Okay, so this is the benefit of learning heat transfer. It's very fundamental. I also like to think of heat transfer when I cook. I like to cook. I like to eat too, as you can see. So when we cook, so many modes of heat transfer taking place. It's fantastic, really. And your mind starts thinking, okay, how is this heat getting transferred from the vessel onto the contents of it? You know, you have an oven in your house, you're sticking into it something. How does it get heated up? What are the modes of heat transfer that are taking place inside there? Can I have heat transfer in vacuum? Absolutely yes. So these are all questions I hope will be provoked in you as we go through this semester. Okay, so that's the motivation for learning heat transfer. What we will be doing is we will be learning 3 things in this course. Conduction heat transfer. Okay, so let me write it out. So conduction. Then we'll be learning about radiation heat transfer. And the last one is convection heat transfer. Okay, 3 things that we will learn. We will start off with conduction because, in my opinion, this is mathematically the more simpler of the 3. Okay. Then we will go into radiation heat transfer, which is more physics-based. Lastly, we will go into convection heat transfer, which is experimental, because you have fluid flow, and whenever you see fluid, it's the scary science, fluid dynamics. I hope all of you have taken fluid dynamics. I'm assuming you have. Certainly you have. So we will use a lot of aspects of fluid dynamics, okay, to study convection heat transfer. Boundary layer theory, for example. What is boundary layer theory? I'm sure that these are topics that might have been glossed over when you took fluid dynamics. I will go into the details of boundary layer theory for one lecture, just to make sure we are all on the same page. Okay? So this is the sequence in which we will be looking at this course. And inside conduction, you're going to start off with one-dimensional conduction. Then we will look at conduction in multi-dimensions. We will look at unsteady conduction. We will look at semi-infinite bodies. Okay, how is heat conducted through the core of the Earth onto the surface? That's an example of a semi-infinite body, very large depth, right? When we go to radiation, we will look at different types of things in radiation like absorptivity, emissivity, and we will also look at radiations in enclosures, how these modes of heat transfer account for in enclosures. Enclosures are closed surfaces, okay? And then lastly we come to convection, where we will look at the two types of convection, forced convection and natural convection. Natural convection we will not spend too much time. I have penciled in one lecture, but I doubt if I will get to it. Forced convection, you can have external flow over flat plates. You can have internal flow through a pipe, that's internal flow. So for all of these things, we need certain information that comes from courses that you have taken in the past. Okay, so I'll point out to those resources when we get there. So that's our main aim, 3 things, just 3 things, that's all. Whole semester. And only one equation for everything. First law of thermodynamics. That's it. You can go home. Okay? So which leads to the obvious question, okay, what is the difference between what you learned in, what is thermodynamics 3500, 3501, right, 3501, and what you're going to learn here. Okay, so ME what exactly am I going to do in 4510, which I haven't done in 3501. Let's take a look at the first one. Okay, so you've come across the first law of thermodynamics in the thermodynamics class. Let me take a control volume, closed control volume. Okay, CB, control volume. Let's say that there is a net rate of energy transfer into the control volume in the form of heat. Okay, so there is Q dot net. This is hopefully the symbol that you used in thermodynamics, because we're going to switch them all around. We're not going to be using these symbols anymore. Okay, just for this lecture, we're going to be doing this. Then let's say that there is some useful work output, net work output coming out of the control volume. There is a certain amount of energy that is stored within the control volume, E control volume. So Q dot net is the net energy transfer in the form of heat. W dot net is the net energy transfer out of the control volume in the form of work. And E control volume is the total energy within the control volume. And I'm following the sign conventions that you might have come across in thermodynamics. Heat into the system is positive, work out of the system is positive. Why is the sign convention followed? It's because of James Watt, the steam engine. You put in heat, you get work out, the wheels move. Right? So with all these elements, the first law can be written as the following. Rate of change of energy within the control volume is Q dot net minus W dot net. What did you do in thermodynamics? In 3501, and this is my broad assumption. Okay, I've taught thermodynamics in the past, and this is typically what we used to do. So you would have learned to model W dot net, right? You can have work done due to a gas expanding within a piston, so you can have PdV work. You can have work due to a spring, maybe. You can have work due to voltage and current combined together, so VI work, okay, electrical work done. And these are not, you can have shaft work, right? Torque times angular velocity. So I'm assuming in 3501 you've looked at all these things. You've tried to model the situations using all of these ideas, so you've learned these things. You might have perhaps also learned about ECV. This is the total energy within the control volume. Which can be broken out into mechanical energy, then you can have thermal energy, which is what we are going to be spending our time on, or internal energy, let's say internal energy. Internal energy is actually split into two things: thermal energy, which is the energy possessed by a body due to its temperature. So you can have sensible thermal energy. Maybe the contents in the control volume are changing phase, so you can have latent energy, right? So you can have all of those things sensible. And you can also have maybe a nuclear reaction taking place within the control volume. Maybe you can have chemical bonds being broken, new friendships being formed within the control volume. So chemical energy, nuclear energy, all these kinds of other microscopic forms of energy. You would have learned all these things in thermodynamics, at least to a certain extent, maybe not the entirety of it. So this is also stuff that you already know, or at least you're familiar with. Q.net. Here is what could have been done in thermodynamics. Maybe given W.net, given the total energy within the control volume, using the first law you would have calculated Q dot. One thing. Or maybe somebody gave you some basic equations. Okay, hey, here is equation for conduction heat transfer. Take that, calculate Q dot from that. Or convection heat transfer or radiation heat transfer. So you would have been given some equations, you would have calculated Q dot, or you would have calculated Q dot based upon energy balance. That's done in 3501 to a certain extent. So just calculate. Without modeling how this comes about. What are we going to do in 4510 is we're going to focus on Q.net. That's our whole course on one single variable. And we're going to see, okay, how exactly do these equations come about? And maybe if you are not used to these equations, okay, now you'll get used to these equations. What's the math behind it? What's the physics behind it? Okay, now I know the math and the physics. How do I apply to something that is engineering? So that's what we're going to be doing in 4510. Okay, so in 4510 we will learn to model Q.net. Makes sense to everybody? I'm going to slide this panel up. If maybe I could request one of you, can one of you take screenshots of my board work so that I can post that on Carmen as well? Just take a photograph of it, if you want. I will post notes anyways, so it's not completely necessary, but if you do, and if you send it to me, I'll be more than happy to post it on Carmen, on top of the video. Alright, so what I want to do now is, before going into looking at Q.net and so on, I want to first of all change our mind. In heat transfer, we will not use the symbol Q dot, we will use Q. What is this Q? This is the energy that is transferred in the form of heat transfer. in the form of heat transfer. Which begs the question, what is heat transfer? So here is a convenient definition for heat transfer. This definition is based on the work of James Clerk Maxwell, and the definition is as follows. Heat transfer is thermal energy in transition due to a spatial temperature difference. I'm going to write it out. So heat transfer is thermal energy in transit which means it keeps on moving, it doesn't rest, okay, due to a spatial meaning XYZ coordinates, for example, or polar coordinates. So in space, spatial temperature difference so this is heat transfer. What is thermal energy? We just briefly spoke about it. It's the energy possessed by a body due to its temperature. So this is thermal energy essentially. It is one of the components of internal energy. Okay. The one and only thing that you want to take from this course is the following. Direction of heat transfer. Anybody? What's the direction of heat transfer? Yes. Absolutely, that's it. You're tuned to it from the day you're born. You think something is hot, don't touch it. Something is cold, maybe not too long, right? But the heat transfer is always going to take place from hot to cold. From T high, which is a region at a higher temperature, to a region at a lower temperature. All of you still okay with the way things are written on the board? Any issues with the handwriting? People in the back? Everything fine? Thank you. Units for Q. It's the rate of heat transfer. Okay, so this is the rate of heat transfer. So heat transfer rate. Okay, that's the name that we are going to give for this. Okay, this is the rate of energy transfer. I should make a mention here. The rate of energy transfer in the form of heat transfer. Okay, that's Q. It's energy per time. Energy is in units of joules. Time, seconds. So this is going to be in watts. Okay, SI system. One joule per 1 second. You will also come across another creature in this course very often, something called as heat flux. Q double prime, which is called as heat flux. Which is nothing but rate of heat transfer per unit area. Which means that this is going to be in watts per meter square units, SI system. could be kilowatts, megawatts. Instead of meter square, I could have millimeter square, but the base unit is meters, the base unit is watt. Okay? So that's it for the units. We will also look at the metric system, the FPS system, the foot-pound second system, in which case, in the rare instances when I solve problems of that sort, Q will be in British thermal units, BTUs. Then you might have this heat flux as BTU per second per meter square. Okay. Sometimes Q will also be in the form of horsepower. You would have seen that in thermodynamics. So there is a conversion between British thermal units and horsepower. Horsepower is once again due to James Watt. Okay, there is a certain specific definition, okay, horsepower, and then converts it into watt, which is again due to James Watt. So all of this, we owe the existence of heat transfer to James Watt. At the end of the semester, you can fan him in the SEIs. All right. Now, I want to briefly talk about the different modes of heat transfer. Okay, so the modes of heat transfer. HX, heat transfer. You have seen these definitions since maybe a few years, probably. Again and again, maybe basic physics classes would have talked about it. Thermodynamics, hopefully they mentioned it in passing. Conduction heat transfer, first mode. This is energy transfer due to molecular interactions. Molecular interactions. Between hot molecules and cold molecules. Hot molecules have higher kinetic energy. This comes from the Boltzmann law. So if you increase the temperature of a certain molecule, it's going to be in a very highly excited state. So it has all this velocity that it wants to flap around and show off. It starts striking other neighboring molecules, transfers a certain amount of its energy. So if a neighboring molecule is sitting there minding their own business, this fellow comes and pushes that guy. The neighboring molecules get a certain amount of kinetic energy. This keeps transferring throughout. Okay, so this is molecular interactions. The thing you want to remember, in conduction, there is no bulk motion of the molecules. What is bulk motion? Bulk motion is macroscopic motion. Macroscopic motion is motion that is visible to us. I have water flowing through a pipe, that's bulk motion. But I have a glass of water sitting on the table here. Is there motion? There is. If you have the capability, you can see the molecules which are present in this glass of water, or I think I had that carafe there, somebody left it there. The molecules in there are still going to be moving around, but the motion is not visible to us. It is microscopic in nature, Brownian motion. And if I start heating up the contents of the bottle or the glass of water, then the molecules will start having greater kinetic energy. They will collide with molecules with lesser kinetic energy. That is still microscopic motion. That is not macroscopic motion yet. Okay? So, when you have conduction, there is no bulk motion, but microscopic motion is allowed. I'm going to push this panel up. conduction in solids can take place due to two things. One is called lattice vibrations. Typically in solids, you're going to have the molecules and the atoms arranged in nice arrays. Okay, one array after the other. And this is called as a lattice, an arrangement of molecules in an array. When you start heating up one side of the body, one side of the solid body, these molecules will start vibrating. They are connected to the neighboring array, so they're going to transfer their vibrations. And the mode of transfer is called as phonons. Not important. This is just for your information. If you want to look it up, please do. Okay, we are not going to be looking at that. That's one way of transferring heat in solids. There is another way which in metals is much more predominant, using free electrons. If you look at aluminum or steel, if you look at the molecular structure, they will invariably, because of the way they are, material property, they will have electrons that are not bound by the atomic cloud. These guys are free agents. They can do pretty much as they please. You heat them up, they're going to have kinetic energy, they're going to start scooting around, strike the next one. And if you look at metals, they have a larger number of free electrons compared to maybe a ceramic. So metals have the capability to get much hotter than ceramics, for example. And in ceramics or insulators like wood and so on, the major mode of heat transfer is through lattice vibrations. So there's still some heat transfer taking place in insulating materials, but not to the extent that free electrons allow. Once again, these are very peripheral explanations. We will not be going into the physics of it as yet. Okay, so hang on to it. Conduction in liquids and gases, which are commonly called as fluids, takes place due to molecular collisions. So in the fluids, due to molecular collisions, pardon my writing at the end. Once again, this is microscopic motion, this is not bulk motion. You cannot have bulk motion in conduction. Moral of the story is conduction can take place in solids, it can take place in fluids. It's not necessary that it has to be only a solid to have conduction, it can be a fluid too. Okay? Just the mode of transfer of heat or transfer of energy is different in a fluid versus a solid. And we'll be spending a good amount of time looking into the details of it. The other two modes, convection and radiation, I will talk about them in the next class, but I just want to give you a very brief idea. When you have convection, it is essentially transfer of energy between a surface and a fluid in the presence of bulk motion. Okay, so this is energy transfer. Between a surface and fluid in the presence of bulk motion. The bulk motion could either be the solid moving, the fluid staying stationary, or the fluid moving, the solid staying stationary. Relative motion, okay, in the presence of relative bulk motion. And in the next lecture, when I start off my lecture, I'll be very, very briefly talking about convection, very briefly talking about radiation as well. Okay, so in closure, what we did today, introduce the syllabus to you, I introduce myself to you. I hope we get to know all of you. I want to convey that this is once again a challenging course. If you can come to lecture, please do try to come to lecture. We'll be looking at 3 modes of heat transfer. Okay, the class is not yet over. Please sit down. Class is not over yet. I have 2 more minutes. I'll take my time. I'm writing things on the chalkboard. You may perhaps have not been used to writing on the chalkboard, mostly because of the fact that we've been online and so on. So there is a